Hello, everybody. Welcome to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to start jumping into some of the more interesting meteorological phenomena, especially where we're concerned. Things like thunderstorms, lightning, and then tornadoes are going to make up the bulk of this set of lectures. So we're going to start with thunderstorms, so let's jump on in. So what is a thunderstorm? Well, we should remember it's basically just a cumulonimbus cloud with lightning and thunder. Usually these are stem from several kilometers deep layer, what we call conditionally unstable air. We might remember this from when we were talking about air masses a little while back. So that allows us to produce a cumulonimbus cloud, and that instability lasts until either the parcels rise far enough to condense into clouds, or the cloud topped thermals penetrate into the conditionally unstable layer, where thunderstorms rapidly develop and the instability is released. Think of kind of our anvil cloud formation. We'll talk about that here in just a little bit. Now, these aren't, particularly uncommon phenomena. If we look at annual mean thunderstorm days between 1993 and 2018 across the contiguous United States, about, mostly centered down in Florida, and it kind of spans out from there with some differences in places like Denver area, or on the kind of leeward edge of the Rockies, for example. Um, but if we look over the entire world, estimated that there are about 40,000 thunderstorms every day, which equates to about 14.6 million occurrences annually. So this isn't an isolated phenomenon, right? We have thunderstorms all the time. Now, there are a number of different types. We've got single cell, multi-cell, squall lines, mesoscale convective complexes, and supercells. Obviously, each of these has their own associated characteristics. We're going to talk about a good number of them, some with higher severity than others, obviously. So if we're to look at the life cycle of an air mass thunderstorm, so we've got this rising parcel of air that is, reaching altitude, capped maybe by some type of thermal layer. And we can kind of see on this, we'll let this play a couple of times here. But these form in warm, humid air masses where winds are light and large-scale dynamical forcing and upward motion is weak. We need conditions where these types of systems can develop. So if there's a high shear, for example, high wind shear, so high winds aloft, that can kind of kill your storm before it even really starts. Typically, they have a diameter of about 1 to 10 kilometers and lifetimes of about 30 to 60 minutes. And usually what happens here is we'll let this kind of restart here just a second. Kind of reaching the dissipation stage here, but should restart. Okay, here we go. So now we've got an updraft, right? We've got this convective lifting of air where our storm is reaching some type of maturity. As it does so, that anvil feature, or that anvil look, is really starting to take off. We have warm air rising, cold air descending, so a downdraft, for example. And then maybe something cuts off that moisture, or cuts off that energy being fed into the storm, and it starts to dissipate. So downdraft collapses on the updraft. So the downdraft is this, it's the part moving down. The updraft is obviously the part moving up, and it can cut off the cell and prevent further development. So mature air mass thunderstorms contain large raindrops, a strong downdraft, and an anvil of ice crystals. If we recall way back when we were talking about clouds, one of the things that we can look at is kind of the wispy nature of the edges of our cumulonimbus clouds, and that can be indicative of ice crystals being the dominant form of moisture within that portion of the cloud. And we do see that here. Lower down, we see, my little pen tool here. Lower down, we see these kind of chunkier looking, blockier clouds. Those would be more moisture. Over here, we can get a good indication of kind of wispier looking clouds and somewhat throughout here as well. And then at some point, as I said, that downdraft causes your lower level clouds to evaporate. Only the anvil remains after that dissipation, and you're kind of left with a decaying storm system. And we see that in this image off on the right here. Severe thunderstorms are another category. They are thunderstorms that have at least one of the following characteristics: hail with diameter of 3/4 of an inch or greater, winds of 50 knots or roughly 57 miles per hour or faster, or a tornado. Tornadoes, obviously, we'll talk about in a future lecture and shortly after this, but severe thunderstorms are a little bit different. So here we can see, here we can see our diagram here, kind of a characteristic diagram, a very typical diagram of a thunderstorm structure. So severe storms usually form in regions with wind shear, and that wind shear allows the thunderstorm updraft to tilt, so precipitation does not fall into the updraft, collapsing it, which is really important, right? We got talking about that dissipation stage or the decay stage of the storm, and that's kind of initiated by that downdraft collapsing onto the updraft and kind of cutting off the storm. But the severe thunderstorms, that wind shear kind of tilts the system. And as it does so, you kind of reduce that collapse feature. So individual severe thunderstorms can last a few hours rather than 30 to 60 minutes. So there's a few different characteristics there. So we continue looking at this diagram. You see that the entrainment of drier air into the cloud leads to evaporative cooling and the development of in-cloud downdraft. So that's kind of our feature right through here, in-cloud downdraft. Here we've got our updraft kind of feeding the system. Our rain, as we can see, not at the leading edge. Maybe we've got some stratus clouds or something along the lines here. Kind of that larger blanketing type formation. We can see as we get to altitude, we've got that very characteristic shape poking into the, you can see our tropopause here. So troposphere here, kind of poking into our tropopause, so below our mesosphere, which would be up there. You can kind of see it's capped here, right? That's where a lot of that overturning is happening, kind of feeding into that downdraft or rushing out along that tropopause. We've got something, the next feature called our overshooting top, which we see here. It's kind of what we're looking at, that classic anvil feature. And kind of poking up top here. And this is our overshooting top, more or less right there. Marks the top of our updraft. So kind of the highest position that we're getting to with our updraft. Here you can see it reaching all the way up and then turning back down. So this would be our overshooting top right there. So the base of that overshoot region is basically the top of our unstable air package. So we might have increased stability within our air parcel further up. So this is kind of the base of that instability. So this is kind of the diagram, right? This is what a mature severe thunderstorm looks like, and this can generate a lot of different weather, tornadoes, hail, etc., which we'll talk about here in a little bit. But there are a couple of other characteristic features. We've got shelf or Arcus clouds, which we can see this feature here that obviously kind of looks like a shelf, forms when stable air is rising above the gust front. So obviously you've got a lot of pressure differential going on here. Remember, this is a big low pressure system usually, so winds are rushing in. So there's a lot of wind. There's a big gust, right? So that gust front is what we would call that kind of leading edge of the storm. So this shelf cloud forms when stable air is rising above that gust front. And then, sorry, another feature, we have our roll cloud. These form just behind the gust front. So maybe the gust front, if our storm is moving more or less kind of right to left, this is just behind the gust front. And roll cloud because there's kind of some vorticinal or vorticical, I think would be the word I'm looking for, movement. So kind of some rotating flow like we see there. And that can be an interesting aspect of the storm. So the main impetus for a lot of these types of severe weather patterns are this combination of air masses. And we'll see this much greater detail once we get to our tornado lecture, but it's kind of a mixture of a few different things. We've got this moist air coming up from the Gulf. These southerly winds at the surface bring warm, humid air from the Gulf of Mexico. We've got southwesterly winds at mid-levels bringing hot, dry air from the desert. And we've got these westerly winds at high level bringing cool, moist air from the Pacific. So that upper level moist air from the Pacific has an environmental lapse rate that's near the moist lapse rate. That mid-level continental tropic air that's coming from Mexico has an environmental lapse rate near the dry adiabatic rate. And then that low-level maritime tropical air from the Gulf is warm and moist. So you smoosh all these together and you've kind of got the recipe for storm development. Now, if we were to look at this in kind of a profile view, a cross-sectional profile view, so this is what we call a sounding chart. You can see we've got our moist tropical air down here, our continental tropical air down here, which is drier and hotter, and our moist polar air over here. So you notice there's kind of an inversion that happens right about here. We can see our environmental temperature profile changing here. And then this is our air parcel temperature here. So we've got a lot of different things going on here, right? And we're not really going to dive into soundings too much, but just for, kind of continuing to paint the picture here, this parcel is more, in this case, than 10 degrees warmer than the ambient air from 500 to 200 millibars. So our millibar range here. And we're seeing kind of that difference in temperature. Here is kind of what we're talking about. And this sounding can give updraft speeds of nearly 100 miles per hour. So the air moving up into the parcel can reach speeds upwards of 100 miles per hour. It's pretty astonishing. So we move into multi-cell thunderstorms. So these are clusters of cumulus cells that are observed when upper winds differ by about 10 to 20 meters per second from the surface. So we can see over here, that's just a single cell thunderstorm. Not to say boring, but just a single cell thunderstorm. Can pack quite the punch. Sometimes you get them kind of, I guess you could call daisy chaining like this, where you see tons and tons of thunderstorms. Each one of these red and yellow and orange blotches there are their own thunderstorm, and it's kind of merged into this massive wall. So basically you get cold air from the downdraft of mature cells that undercut and lift the surrounding air, initiating adjacent new cumulus cells. So you've got kind of this feedback loop where you've got this cold air downdraft from the upper portions of our cumulonimbus cloud, right? If we're thinking of it, our cumulonimbus cloud, the typical anvil shape we see here. Bring it across here. We've got that warm updraft and that cold downdraft, and our precipitation is kind of maybe from back here to here. So it's that cold downdraft from that mature cell that's kind of undercutting and lifting some of that surrounding air, kind of pushing it out of place, causing it to rise, forming adjacent new cumulus cells. We've got squall lines, or another feature. So here you've got kind of this really, really intense set of storms that can form ahead of advancing cold fronts. So here's our cold front. We see kind of pushing in here. We've got this warm, moist, unstable air. That instability is really what you want. So basically what you've got is the system that forms when upper flow develops waves, and you can kind of see these wave patterns here downwind of the front. They kind of organize in the kind of leading edge of maybe a big cold front system. So we can see in this diagram here, the squall line is made of several thunderstorms, can be more than 100 miles long. They're often 50 to 150 miles ahead of an advancing cold front. So you've got this large area of stratiform or stratus clouds, which often trail the squall line, can develop into rainy systems that last longer. Think of like your longer drizzles. You've got this water vapor rising, forming precipitation. Precipitation evaporates into dry air, cooling even more. And then you've got this cooled, heavier air down here that's plunging downward and blasting the ground with high winds. So it's a pretty dynamic and intense system that looks like this. This is what we would call a squall line. So you can see this big band of very intense storms. And if we could see, unfortunately we can't right now, the wind speeds as well, we would see that there's a massive difference. So higher storms, higher winds along this squall line. Storms can also help initiate new storms. So as storms decay, that gust front can trigger rising air and new thunderstorms adjacent to the old one, or more than roughly 100 kilometers away. So you've got, if we look over here at one, right up here, air flows downward from a thunderstorm like this, kind of rushing out. That's that downdraft, that cool downdraft, and outward when it hits the ground. So I can kind of kick up dust. And then advancing air, cooler air, pushes up warmer air, maybe along the surface, a different parcel, leading to cloud formation. And those cool winds can travel more than 100 miles and keep on going long after the original storm dies. Here again. And collision of these gust fronts often push air up, vertically rise it, and trigger these new storms. So old storms can function and trigger new storms. Now, you can see here kind of what that is in just like a two-dimensional profile view, where you've got these, cell 1 is starting to die, you've got these downdrafts. Cell 2 is being fed by those downdrafts. And cell 3 is starting to grow. New storms can also choke off old storms. So you can basically cut off the moisture supply to some of these big thunderstorms as new storms are starting to develop. So new cells cut off inflow of low-level moisture to old cells, then cause older cells to die off, leaving new cells to develop. And line of storms moves to the right of the individual cell motion. So you can see kind of here, we've got these new cells. So our line movement is this way. So we've got these new cells that are starting to pop up. You see here, and cut off some of these old cells from the moisture supply that they need. Hazards associated with thunderstorms, lightning, hail, microburst winds, flash flooding, and tornadoes are among the biggest. I'm not really going to dive into lightning, hail, and tornadoes because I've touched on those in other lectures. I'll link those in the description below. But we'll start off with microbursts. So there's a couple different types. There's dry and wet microbursts. Microbursts basically happen as you've got a couple things going on. You've got this evaporation of rainfall cooling the air below the cloud. That heavier cooled air accelerates the downward momentum of the storm. That falling rain accentuates the downward acceleration. And then you've got this rapidly sinking air that hits the ground and fans out with these high winds. So this is pretty common in the desert Southwest during the summer, primarily in places like Arizona. We look at our little graphic here on the side. You've got step 1 and a dry microburst. I'll switch to black here. You've got air below a shower or thunderstorm that's very dry. That rain evaporates into dry air, cooling that parcel down. The heavier cooled air plunges downward, and it might initiate a dust storm. Now, wet microburst, you've got dry air entering the thunderstorm. That rain evaporates, cooling the dry air. That cooled, heavier air plunges down, and heavy rains often hide the microburst. So it can be pretty wild when you've got one of these little microbursts, these tiny little cells that can carry pretty intense rain along with it. I've lived through some microbursts when I was living down in the Southwest. It's pretty astonishing to see just how much rain can be dumped right over top of your head, but then you can see the edge of the storm in every direction. Or here we can see the example of a dry microburst. So we see there's no rain shaft, no rain coming down, but we are seeing dust being kicked up. So we can see air below that shower thunderstorm is very dry, kind of plunging that cooled air down. So it can initiate things, some certain dust storms kind of on the leading edge of a storm or a thunderstorm. We call those haboobs, Haboobs. We'll probably talk about those here in our next set of lectures when we talk about some extreme weather phenomena. Here we can see another example. See this very localized, intense downpour, and you can kind of see all edges of the storm. Here we are in the Phoenix metropolitan area. You can see some of the mountains in the region near campus for the Arizona State University campus. So microbursts can be pretty dangerous. There's obviously an aviation risk. They're a serious hazard to pilots. Rapid change in the winds can lead to a loss of lift during takeoff and landing. And the microbursts have caused several crashes of jets as well. So basically you've got this air that's rushing out of the system and cooling and working with that warm air. And basically can kind of turn a plane from thinking it has a headwind, as we see in one here, to changing it to a tailwind. But that tailwind causes the speed of air moving over the wings, what's generating that lift force, the buoyancy force that it's trying to overcome forces of gravity, and can kind of lead to a crash. So it can be pretty dangerous because of that sudden change in wind speed and direction. We've got these big things called mesoscale convective complexes. These are basically state-sized areas of thick raining anvil that form from organized storms. You've got basically a massive cumulonimbus complex here. These usually form during evening and last the entire night. Lead to 2 to 5 inches of storms, and they actually produce half of the Midwest's summer rain. So these types of mesoscale complexes are not uncommon, especially in our neck of the woods. This map and the dots of it kind of hurt my geographer brain, but you can see here's Wisconsin up here. Dots are not a good way to make a map if you're ever trying. But here we can see, here's Wisconsin, kind of rolling over Kansas, Nebraska, into Missouri, Oklahoma, and Arkansas, and the southern extent of Iowa. But these types of storms are pretty common where we're at, and they produce some pretty serious issues like flash flooding. This was a case in Big Thompson. This is the Big Thompson flood in Denver. That was pretty detrimental, and there's a whole lot of different things going on, flowing into a pretty steep-sided basin, floodwaters hammering this area near a little bit northwest of Denver. So pretty big issues if you're in the desert. These can lead to flash flooding and things like desert washes. Definitely not good. If you're in the upper Midwest, these can, basically flood roads, and, you can become stranded. So flash flooding is a major risk with these types of massive systems. And then things like supercell thunderstorms. We're not going to touch on these just yet. Those are going to come when we start talking about our lightning and tornadoes, which are coming up next. So these are entire cumulonimbus rotations, usually counterclockwise where we're at. So think of these large, basically this entire system is rotating in some type of counterclockwise rotation. We'll talk about those here in a little bit. But that kind of touches on thunderstorms for us. What is a thunderstorm? It's a cumulonimbus cloud with lightning and thunder. It's generated from a deep layer of conditionally unstable air. There are several different types. We touched on what most of those were. And they can pose a pretty serious hazard to public safety, transportation, and commerce. In the next couple of lectures, like I said, we're going to talk about lightning and thunder and then tornadoes. So stay tuned, and I'll see you in the next video. Thanks.